Good morning, everyone. While I pull this up, I was thinking Dr. Schumacher didn't share with you that the subject is hematocrit was 91. He didn't know that Lance Armstrong was a member of that study. I was thinking when he showed that. But, okay. Too early? Too soon? Individual response to training at altitude. Some of you may have read the paper we published in 1998 looking at some of the concepts involved in this response, and largely those were centered on erythropoietic mechanisms that relate to performance. I'm going to talk about something a little different, which is more the training effects side, which I don't think gets as much due in that study, and particularly with this. So to go through this, I want to start with a little bit of a personal story. It's near and dear to my heart. That's actually a picture of me many kilograms ago, many more hair follicles ago. This picture happens to be from the 1987 Nevada State High School track and field meet. And if you're not familiar with Nevada, it's in the American West. It's a fairly large state. From bottom to top, it's over 1,000 kilometers, so it's pretty large. In the south, it's very much like Doha. It's desert, very hot. You go up here in the north, if you've ever been to Lake Tahoe, very beautiful, very mountainous, more of an alpine type of setting. Now, the state meet this year happened to be in Reno, and Reno, if you're not familiar with it, happens to be at an altitude of 1,450 meters. Where did I live? I live down here very near. I was born in Las Vegas, grew up there. Las Vegas is at an altitude of 650 meters. This picture was taken, we run kind of bastardized distances in the United States. This is a 1,600 meter run. It's the closest thing we have to the mile. This is a little after the halfway point, and I stayed in the lead till about 20 meters to go when this guy here decided he would pass me and win the race. And for many years, tried to figure out, how come this guy beat me? I figured I was better than him. I knew my training was good. I felt like I should have been there. Well, the only thing I could come up with after a while is that this guy was from Elko, Nevada. And Elko, Nevada happens to be at 1,550 meters. So either there had to be something about him that made him better able to perform at the altitude of Reno, or something about me that made me where I couldn't perform there because of this difference. And so largely spurred, the career I've taken to date. I'm not bitter about it, by the way, but it's largely kind of primed some of the studies I'm going to show you about. So here's some pictures of faster people. Obviously, the 1968 Mexico City Olympics really kind of focused our attention on competing and training at altitude. There's two quotes from studies in and around there that really kind of hit a nerve with me. The first one, D.B. Dill and Bill Adams said, highly trained endurance athletes appear to be handicapped to an unusual extent at altitude compared to lesser trained individuals. And the other one is by Buzzkirk, who said VO2 max is reduced about 1% for every 100 meters ascended above 1,500. So basically the concepts they're talking about are susceptibility, who's more susceptible to declines in performance at altitude, and then also threshold altitude. How high do we have to go? Is 1,450 meters in Reno high enough to slow down performance? So basically, let's kind of walk through these first. First off with susceptibility, this is data from John Lawler. What he did is he did a VO2 max test in normoxia and a VO2 max in hypoxia. This was 3,000 meters, I believe. And he obviously had a range of individuals in terms of fitness. And he saw, again, confirming what Dylan Adams saw, a very tight correlation between the change in VO2 max and your initial VO2 max at sea level. But what Lawler did is he tried to go a step further and say, what's the mechanism behind it? And what he looked at was arterial oxygen saturation. And he found the individuals who had the biggest decline in saturation, or in VO2 max, were the ones who had the lowest saturation. And so, your couch potato over here, who had no change in performance, he was the one who was able to maintain his saturation basically the highest. So Dr. Schumacher already showed you, a cartoon that's very similar to this. We know that arterial saturation maintenance is dependent on at least a couple of different factors. One of them is going to be the transit time of the red blood cell through the lung. And as you go from left to right, there's only a certain amount of time that the red blood cell is going to be in contact with the alveoli. And during that time, you're going to see PO2 rise. And even in a quarter of a second, which might be your transit time during maximal exercise in a normal individual, you're going to have enough time to fully oxygenate your hemoglobin. This is work by Jerry Dempsey and some others have shown, though, that you have a reduced transit time in some athletes who have very high cardiac outputs. And so in that case, you're not going to have time to fully oxygenate the blood. And so some people are going to desaturate during heavy exercise, even at sea level. And so if you think about it, if we talk about untrained people, and this is the oxyhemoglobin dissociation curve relating PO2 with saturation, when you go to altitude, you're going to have a given change in PO2, and the untrained individual who has their saturation very high, even during maximal exercise at sea level, they're going to see a very small change in saturation. Now, what kind of stinks for the trained athlete is if they desaturate at sea level, they're going to be on this steeper downslope of the oxyhemoglobin dissociation curve. So a given change in PO2 is going to mean a much larger change in saturation. So in terms of susceptibility, this may explain why trained individuals are at least more susceptible to declines in performance at altitude, but it's not that simple. If you take it another step and look at threshold altitude, here's, again, work by Buskirk and his group showing here's the percent of VO2 max at 362 meters, which is the altitude at Penn State where they did these studies. And they did a series of tests, and I have feet and meters because in the United States we're metrically challenged, so I have to put both of them up there. And they show that basically they updated in 1982 from what they said back in the 60s. Now we're down to 1,250 meters where we're going to see a decline, significant decline in VO2 max. But in this study, what they did is mainly use very average college kids. So not really highly trained athletes. And so Nick Tarados came along in '85, and he said, well, we know that trained and untrained are different in terms of their ability to maintain arterial oxygen saturation, so maybe we'll see a difference. And so his data points are actually the circles. And if you look at the untrained individuals, they're not seeing a reduction in VO2 max until maybe 1,200 meters, whereas the trained individuals are seeing a reduction in VO2 max at a much lower altitude at 900 meters. And then Chris Gore came along and said, well, you know what, let's go even lower than that. And so you did your study at 580 meters, correct, which is Canberra's altitude, and so showed essentially the same thing, that even at 580 meters, and again, you got to realize how low that is. It's an altitude that really wasn't considered to be limiting to performance or VO2 max at that point. And in trained individuals, we're seeing a strong difference. So based on that, I came up with a thought and said, well, we know that all trained athletes don't desaturate. Only some of them do. Some of them are able to maintain their saturation during heavy exercise quite high. So what if we take the trained group and we divide them into non-EIH, in other words, individuals who can maintain their saturation high, and athletes with exercise-induced hypoxemia, the ones who desaturate. And the theory was we should see that these individuals respond to altitude more like the untrained people in the Gore and Tarados study. So basically the same graph, and these are the two data points from our study. And hopefully what you can see is that we did ours at 900 meters, and you can see that the high sat athlete doesn't have a significant decline in performance where the low sat athlete does. So if you're able to maintain your arterial oxygen saturation high, in my opinion, that is the key variable to look at in terms of how well an individual is going to be able to maintain VO2 max at altitude. So it really isn't dependent on fitness or training status. I think it's more dependent on arterial oxygenation status as being a key player. And at least with the concept of threshold altitude, this is John Werland's study, where he took a number of these studies who have looked at a range of altitudes and the decline in VO2 max. And this concept of threshold altitude you really can't apply anymore, particularly when you're talking about athletes. It's pretty much as soon as you go up immediately from sea level, you're going to see pretty much a linear decline in VO2 max. So what's the next step? The next step is, well, I'm interested in performance. Do we have VO2 max competitions? Not really. We have races, right? So the next step is, can we take this relationship between saturation maintenance and VO2 max decline and take it one step further to performance? So the next thing we did is we took athletes and divided them up based on their saturation response to maximal exercise. So we had a group of low sat athletes and a group of high sat athletes. And basically the dividing line for this is around 90%. If you're below 90%, and we had a buffer zone in between at 2%. So the high sat athletes were 92 or above, the low sat athletes are 90 or below. Throw out the ones in the middle to make sure we don't have any overlap. And we did two different things. One is we took them in the lab, and we, instead of doing a max exercise test, we ran at their 3,000 meter race pace. So a simulated race pace on the treadmill. We did 4 minutes in normoxia, and then we did 4 minutes in hypoxia, and we looked at the change in VO2. Low sat athletes, as we saw with VO2 max, are going to have a bigger decline in VO2 than the high sat athletes. Well, what does this mean to race performance? Well, we did the same thing as well with racing, where we ran 3,000 meter time trials. We did one at sea level, put them on a plane. We flew out to Utah, did another one 30 hours after arrival at 2,100 meters. And by extension, we see that the athletes who desaturate have a significantly larger decline in performance than the athletes who are able to maintain their saturation. So at the end of the day, I think if you can measure one variable that's going to talk about how an athlete's going to perform at altitude and how they are, I think, going to be able to train at altitude as well, saturation is going to be one to look at pretty closely. Interestingly, you might say, well, does ventilation play a role? In other words, is there anything you can do about it? If you desaturate, well, it kind of sucks for you. If you go to altitude, is there anything you can do about it? Well, one interesting thing is if you look at the low sat athletes, they tend to have a lower ventilatory drive, if you will, a lower ventilatory response to exercise. So we thought, well, what if we could do something to get these group of athletes to breathe more? If we could get them to breathe more, then it's like what Dr. Schumacher talked, we're going to have a higher driving pressure across the lung to help saturate the hemoglobin. So we searched around for some ventilatory stimulants, and probably the simplest one we came up with was caffeine. Caffeine ends up being a very potent ventilatory stimulant, been used for a long time, especially in neonates, to try to get them to avoid apnea. So what we did is we took athletes who had EIH, athletes who desaturated, and what we did is we did a test with a placebo, but then we also gave them 8 milligrams per kilogram of caffeine. To give you an idea, for a normal size individual, that's about 5 or 6 cups of American coffee. So it's a pretty good jolt to the system. And then here's the data that we saw, and each of these panels are set up the same way. This is percent of VO2 max, so you have workload on the x-axis. We have ventilation, end-tidal oxygen pressure, the ventilatory equivalent, and saturation. And in each case, the placebo is the dark circles, and the caffeine is the open squares. And if you look across all 4 panels, essentially at any workload, you're seeing that the caffeine, with the higher ventilation, is having higher oxygen partial pressures, and we're getting saturation higher, at least submaximally. But then notice what happens as you get to max. Even though ventilation, this is kind of the opposite of what Chris talked about yesterday, even though ventilation is statistically higher here, it's much smaller magnitude than what you see down here. This is about a 10% increase. This is about a 4% increase. So the ability to increase ventilation is getting tighter as you get closer to max. And the differences we see in saturation, at least during maximal exercise, aren't going to be that different. So if this is going to play a role, maybe it's more so in submaximal exercise than maximal. But so why would caffeine have an effect submaximally, but then when we get to max exercise, we can't increase ventilation more? Well, we kind of thought, well, maybe we've got some athletes who are flow limited. And if you're familiar with how the pulmonary mechanics work, this is a graph that shows ventilatory flow as a function of volume. And the way you read this is you have expiration is on the top half of the graph, inspiration is the bottom half. So this is what's called the maximal flow volume envelope. If you go from TLC, or the lungs completely full, you blow out air as hard as you can, it's going to follow a path like this until you hit residual volume. And if you were to inspire as fast as you can, the flow volume relationship is going to look like that. The dotted line represents a tidal flow volume loop during maximal exercise. And what you see is that with expiration, you're going to reach a point where the tidal flow volume loop is going to meet the maximal flow volume loop. So in other words, you've reached the capacity to generate expiratory flow. No matter how hard you push, you're not going to be able to increase flow beyond this. So perhaps during maximal exercise, the reason that these athletes couldn't increase ventilation, even with this huge dosage of caffeine, was because they're flow limited. So we decided, well, let's do a study where we take people who look like this during maximal exercise and people who look like this. So these are flow limited, these are non-flow limited. And if we gave them some ventilatory stimulus like caffeine or like hypoxia, which one do you think would be able to increase ventilation? The one on the left or the one on the right? Well, probably, hopefully, the one on the left. So if you look at it, here's what you would call their ventilatory reserve or their ventilatory capacity. Obviously, a lot more room here if they could increase pressure compared to what this individual could. And then the other thing is that this individual could shift their lung volume to the left. That's going to give them more room to increase pressure here. There's some consequences with this, though. As you shift more towards total lung volume, it costs more. It's metabolically more costly. So we did a maximal exercise test in non-flow limited and flow limited athletes, and what did we find? Well, if you look at ventilation, the non-flow limited athletes, as we thought, were able to increase ventilation across every workload. But the flow limited athletes, even as low as 50% of max, when you wouldn't think that they're flow limited, still were unable or didn't show an increase in ventilation. One of the interesting things is, notice the non-flow limited athletes. This is in normoxia, this is in hypoxia. So during maximal exercise in normoxia, notice their ventilatory levels were equivalent to what the flow limited athletes saw at 90%. And these are athletes that are essentially the same size, same anthropometric, so we wouldn't expect there to be a difference. So when we looked at ventilatory drive as a function of end-tidal CO2, what's interesting is the flow-limited athletes have a higher ventilatory drive than the non-flow limited athletes. So when we looked at it, and we've seen this consistently across our studies, where we look at flow limitation, is the flow limited athletes, we don't like to think of them as flow limited. It's not that the maximal envelope is constraining their ventilation. We think it's the other way around. We think they have a higher ventilatory drive, and they're actually flow maximized. Okay, so they like to increase their ventilation to, even at low workloads, to take advantage of the mechanical room that they have. So kind of the next step, and this is some new data to share with you, is we kind of asked the question, well, how might these all play together, at least with flow limitation, to affect the response to altitude training? So we came up with a hypothesis of flow-limited athletes will display poorer metabolic and performance responses to chronic altitude training compared to non-flow-limited athletes. And the thought was maybe that this is going to happen either because A, they're going to train slower at altitude so that they minimize that flow limitation or to minimize the work of breathing. In other words, if they're flow limited, when they go to altitude and they have this stimulus to breathe more, maybe they're just going to be like, well, wait a minute, we're going to back off and train more slowly. The other thing is maybe they're not going to have as good of a training response because they can't increase ventilation, they're not able to defend their saturation as much. So they're going to desaturate more during exercise at altitude. And as a result, they're not going to be able to get the same sort of training effect. Everybody kind of with me on this? Does that kind of make sense? So what we did is we went and we looked at some old data that we happened to be sitting on that had flow limitation measures, pulmonary mechanics measures in athletes who've taken altitude. And in total, we've got 18 of them that we can analyze that find that are 8 that are clearly non-flow limited and 10 that are clearly flow limited. And so we put them in the 2 groups. Each of them did a 28-day modified live high, train low, where one of the cohorts lived at 2,500, trained at 1,250. That's 14 of our athletes. We had another group live at 2,100, trained a little bit lower. That's 4. And we actually have 4 athletes at altitude right now that we're going to test when we get back. And hopefully we can add to this and get up to 22. Then we're closer to Chris's magic number that we need. And this is kind of interesting. So here's HVR. Here's their hypoxic ventilatory response. Both groups show a strong, significant increase in the hypoxic ventilatory response. So they both have pretty good ventilatory acclimatization. What about ventilation at VO2 max? And this should make sense. The non-flow limited group with that ventilatory acclimatization was able to increase ventilation at VO2 max. Here's the flow limited group. Nothing. No change. Well, what effect does this have on VO2 max? Well, same sort of thing. In the non-flow limited group, we see a significant increase in VO2 max, no change in the flow limited. And what's really kind of cool is if you look at the individual data points. So if you look at all of the non-flow limited people, every single one saw an increase in VO2 max except for this guy here who just happened to be our highest VO2 max person to begin with. And if you look at the flow limited group, every single one saw a decrease except for this one individual here. So a pretty strong directional response based just on flow limitation status. And then at the end of the day, what are we really interested in? Performance. So in not all of our athletes, but in most of them, we were able to do a 3,000 meter time trial before and after. Only the non-flow limited group got faster. Flow limited group had no change. And again, look at the individual data points. In the non-flow limited group, every single one of them got faster except for this one person here who had no change. In the flow limited group, every single one of them got slower except for this guy here. So if any of you happen to get this paper as a reviewer, be kind when it comes across your desk. So to sum it all up, here's some what I would think are practical recommendations in terms of the individual response to training at altitude. First off, I think saturation maintenance is a key player in terms of determining VO2 max in performance. I think if you can measure one variable, that's going to be the one I'm going to pick. And we've talked a little bit about the erythropoietic response, and a number of people in here have plans. I know Karsten mentioned, where's Karsten? Mentioned the other day that he's got some studies planned to look at it. Ben Levine's tried to look at the genetic response. It's really tough to find anything on the red cell mass side, right? But I think at least on the training side, which is perhaps just as important, your ability to train at altitude, I think we've at least have one measure that's pretty clear that we can look at to try to predict who's going to respond or not respond. If you have athletes who have exercise-induced hypoxemia, there might be an advantage to stimulating ventilation. We've used caffeine to do that. It might be able to help improve saturation during submaximal exercise. That could potentially help these athletes during performance at altitude. And then the last one, our newest data is athletes with expiratory flow limitation, they seem to be less likely to improve VO2 max in performance. Is this a function of reduced training? Unfortunately, we don't have those measures to be able to know. That's obviously going to be the next step. Do they have more dyspnea if you're flow limited? And then I think something that should be looked at is, are there any metaboreflex effects? If they're flow limited, are they now redirecting more blood flow to the lung, less to the locomotor muscle? Is that affecting training on this? So that's what I got. Here's our group. Again, graduate students and the people who gave us money to do the things we've done. So thank you.